All right, team, let's get right into this engineering explainer. Today, we're taking a highly focused, deeply technical look at a crucial piece of our microkernel architecture. Our primary goal right now is absolute architectural alignment across the board regarding SEXNODE's role as our user space cluster coordinator. We're going to look exactly at how cluster management and translation actually work on SexOS through SEXNODE. This whole thing, it's all about establishing deterministic purity over monolithic chaos, and it's going to fundamentally align how we approach our OS design from here on out.
So here's the roadmap for today. We're hitting 5 key areas. First, SEXNODE as the deterministic coordinator. Second, how we're eradicating ring 0 attack surfaces. Third, domesticating drivers with tuxedo. Fourth, our proven loading translation pipelines. And finally, what's next on the horizon? The distributed single image cluster. Let's get to it.
Starting with Section 1, SEXNODE, the deterministic coordinator. To really grasp what SEXNODE does, we got to start right at the foundation.
Let's do a quick reality check referencing Section 1 of our architecture docs. We need to continuously hammer home the strict, absolute, non-negotiable invariance of our single-address space operating system, or SEXOS. Look, guys, this is not a legacy Linux user space. We operate with zero POSIX or Linux assumptions here. We are running a strict, no_stud Rust microkernel environment. There's no libc, no standard threads. You absolutely cannot have cross-protection domain pointers. They're literally invalid by design. All communication is PDX IPC only, and the whole thing is locked down tight using Intel MPK or PKU hardware isolation constraints. SEXNODE is our multi-role cluster node and translator, and it operates strictly within this framework, enforcing these exact rules across the cluster.
Moving to Part 2, eradicating ring 0 attack surfaces. This was a massive architectural pivot for us when we realized just how vulnerable legacy monolithic kernels really are. If you look at Section 2 of our threat model, you'll see we realize that dropping a massive, complex ELF parser right into ring 0 is literally a cardinal sin of capability security. I mean, it creates this huge attack surface before the OS is even fully booted. So we fixed it. We completely eradicated that ring 0 attack surface by abandoning monolithic ELF loading in the kernel altogether. Instead, we extracted the whole shebang: ELF parsing, memory offset calculation, capability graph construction entirely out of the kernel. We offloaded it completely into ring 3 user space, totally managed by SEXNODE. And because SEXNODE takes on all that heavy lifting in user space, the kernel gets to just breathe. Like the spec says, the kernel remains a pure deterministic routing fabric. Its only job now is allocating a protection key, tagging the page tables, and enforcing the capability graph that SEXNODE proposes. SEXNODE is purely a coordinator. This means there is literally no way a malicious ELF file can compromise the highest privilege ring of our system.
Okay, Section 3, domesticating drivers with tuxedo.
Look, we obviously can't rewrite every single piece of hardware driver code on Earth from scratch. But we also absolutely refuse to run Linux natively as a hypervisor, because that would totally defeat the purpose of our SEXOS architecture. So what's the answer? Domestication. Referencing the DDA spec in Section 3, let me introduce you to Tuxedo. Tuxedo is our device driver environment translation broker, and it runs entirely in Ring 3. Think of it strictly as an untrusted guest containment wrapper. It's essentially a cage for foreign chaotic code. The legacy driver actually thinks it's running inside a monolithic Linux kernel. But the reality? Every memory access, every interrupt request is happening inside a hardware-gated segment that we strictly control.
Let's contrast this for a second. The legacy Linux model is a monolithic mess, plagued by asynchronous IRQ chaos and ring 0 vulnerabilities. But under our Tuxedo model, those translated Linux drivers are completely stripped of their asynchronous IRQ chaos. We contain them within strict deterministic ring 3 tick boundaries, and we force them to allocate memory from fake K-Moloch arenas that live entirely in a local ring 3 slab, totally isolated from the actual kernel heap. Mapping out the exact ABI model here is pretty clever. When the Linux driver calls K-Moloch, Tuxedo literally just fakes it, handing it memory from that local slab. When the driver calls IO remap, Tuxedo traps the call and issues a PDX call to our pure kernel to map the physical address to a specific Intel PKU key. And if it calls request IRQ, Tuxedo traps that too, routing the IRQ hardware signal straight into Tuxedo's deterministic IPC queue. That means it doesn't fire asynchronously. Tuxedo is basically a shim, tricking the driver while actually executing our native, safe PDX primitives. Which brings us to Section 4, proven loading translation pipelines.
Let's separate the theory from reality and look at how this actually flows in the system.
For driver loading, this is our proven deterministic 4-step pipeline straight from the sequence diagrams. Step 1. SEXNODE receives the load_Linux driver command. Step 2. SEXNODE issues a PDX call to the SexShop server on slot 1 to actually fetch the driver package. Step 3. It calls our POSIX syscall server, SexEC, on slot 2 to translate that driver via the Tuxedo wrapper. And Step 4. It triggers a spawned PD call to run that newly translated driver as a completely isolated protection domain. Just 4 steps, entirely deterministic, purely coordinated right from user space.
And it's not just for legacy drivers. Per our ELF handling docs, we've got the translate ELF pipeline too. When SexGemini encounters foreign architecture binaries, it routes them right through our native SexGemini compiler toolchain. That translates the foreign code so it can be mapped directly into our native, capability-gated SexOS space. It's how we get seamless integration of foreign code right into our unified 64-bit global memory map.
Finally, Section 5. Next, distributed single image cluster. We've covered what's currently proven, so let's shift gears to our immediate next work.
According to the network spec in Section 5, our immediate next big objective is bridging SexNode's local cluster operations with the SexNet server. Why? To establish remote PDX routing. We're taking our fast, local, lock-free IPC mechanism, and we are going wide with it. Soon, a server on one physical machine will make a PDX call to a protection domain on a completely different machine, and it's going to happen exactly as if it were local.
But what about security, right? If our cluster needs to revoke a capability, like instantly shutting down an untrusted domain, doing it just locally isn't enough anymore. So we're implementing revoke key multicast. This mechanism allows us to perform hardware-accelerated memory capability revocation, literally flipping the Intel PKU bits, synchronized simultaneously across multiple physical machines in the cluster.
By combining remote PDX routing with revoke key multicast, we're basically erasing the boundaries between physical boxes entirely. We're turning the entire physical cluster into a single image distributed SexOS. The whole network behaves, schedules, and secures memory as one single unified computer. It's a massive leap forward.
So here's where we stand today. We've completely eradicated the Ring 0 attack surface. We've successfully caged legacy drivers using Tuxedo. We've proven the SexNode translation pipelines. The foundation is absolutely locked. So my question to you is this. As we deploy remote PDX routing across our network, what is your specific role in fortifying our distributed single-image SexOS? Something to think about as we get back to the code. Thanks, team. I'll see you in the next Engineering Explainer.